Okay, I erased and I redrew the arm here with a little bit more detail. So we're going to say A is the cross-sectional area of the entire arm. And then to be clear, the part that is fat would be X, the percentage, or the fraction, say 0.12 for 12%, which is really low, by the way. 0.12 times A would be the fat cross-sectional area, and 1 minus 0.12, or 0.88 times A, would be the muscle cross-sectional area. So just to be clear, A refers to the whole thing. All right, so here we go. You'd start, and let's see, what do we know? We're going to simply apply delta V to the whole arm, all right, and then the device measures, apply delta V and measure I arm. And what that means is there's a current going through, a total current going through the arm. And the idea is it's divided up between the fat region and the muscle region differently, but the total is all you can measure, right? The device can't tell which electron or which charge carriers came from fat, which came from muscle. It just gets the total. So we apply a delta V to the two ends of the arm, and we just get I arm, I total. And the question is, what is X? What is the percent body fat? And for that, one more thing I'll add is, why is the percentage of that area the same as the percent body fat that the doctor cares about, which is by mass? The reason is, if you have a cylinder like this, and if the fat and the muscle have the same density, then the mass for each one is its cross-sectional area times the length, that's a volume, times the density, which gives you a mass. So both the fat and the muscle have the same density and they have the same length. So the total mass is just proportional to that cross-sectional area. So that's how we're calculating that relative, or the fraction of cross-sectional area that makes the resistance the right way, and calling that percentage the same as body fat composition percentage. Okay, so here we go. Apply delta V, measure I arm. So probably you have an idea. One thing we might want to do is calculate the resistance of each of these two things. Okay, so we wrote our formula for the resistance of a circular cylinder, but really any cross-section that makes a cylinder, that formula applies. R fat, is the density of fat, rho, times the length, which is the length of the arm, L, and then over the area that is fat. So the total area is A, so it's just X times A. All right, if it's 10%, 0.1 times A. And now I'm going to do something tricky, is I'm going to put 2 here, and I'm going to put muscle there. Because it just happened, remember, that fat was 26 ohms and muscle was 13. So it's just lucky that it's a factor of 2 difference. That lets us keep this kind of symbolic, rather than putting big numbers like 13 and 26 in it. We'll just stay symbolic and just call it rho muscle and 2 times rho muscle. Okay. And then the resistance of the muscle part of the arm is just rho of muscle times that same length over, and now the fraction is the 1 minus X. Okay. If this is 0.1, this is 0.9. Right? 10%, 90%. All right, so we have our R's. And now what we can do is get Ohm's law for each one of these two. So let's see, delta V, which is just given, delta V the instrument applies, equals the current flowing through the fat times 2 rho muscle L over X times A. And then we could also say, if we want to think about the muscle, delta V, we don't need to write muscle because the delta V's are the same, equals the current flowing through the muscle times rho M L over 1 minus X times A. All right, now your algebraic instinct is probably, let's set these equal to each other and solve for X. But you can't, because you don't know the current that just flowed through the fat, and you don't know the current that just flowed through the muscle. You only know the total current in the arm. So what we're going to do is the junction rule. Okay, or you could use your intuition and say the sum of this one plus IF plus IM equals I arm. Or you could be formal and write the junction rule and make it look like a junction kind of like this. And they're not identical because they have different resistivities, but you could say I arm is flowing in here. That's what's coming out of the instrument, the current coming out of the instrument. And it breaks up into I muscle and I fat. And then it ends up back, the total has to be conserved. So it ends up I arm again. So using our junction rule, we know that I arm, the total, equals I fat plus I muscle. We know that's true, because you have to conserve charge and current. So we say then we do like I total, or I arm, that's something that we're measuring, so let's keep that in the equation, I arm. And now let's just substitute our fat and muscle quantities, because we know things are going to start canceling and combining together, because they're both in terms of the same delta V, the same L, the same A, etc. So let's go ahead and write that then. So I fat is delta V times XA over 2 rho L. If I rearrange that, delta V, delta V times XA over 2 rho muscle L. Okay, just solving that for IF. And then plus, this is delta V, and I know it's 1 minus X, it's really the only difference. 1 minus XA over 2 rho ML. Oh no, there's no 2 there though. Let's look at it. So this delta V, or this is delta V 1 minus XA over rho LM. Rho ML, like that. Right, okay. And then what we want to do is get a common denominator and multiply things out, and eventually we're going to be able to solve for x, because let's see, what can we do here? How did I solve this for x? Oh yeah, well we measure I arm, yes, okay, so yes, I thought I had to get rid of I arm. So let's go ahead and just combine these. I arm equals, let's make the common denominator would be 2 rho ML, and then it'd be this plus 2 times all that. So we could pull out the common parts, which is delta V and A. So let's see, the common parts are delta V and A, and what's not common is we have 2x and 2 minus 2x. So we have 2 here, that's that 2, minus 2x plus 2x, oh I don't want the 2x's to go away. Oh sorry, we have x and then minus 2x, so 2 minus x, like that. There we go, that looks good. 2 minus x, right? Right, and then we keep going, and I forgot what I'm trying to, yes, so what we're trying to solve for here is we got to get the delta V back in here somewhere. Oh, there's the delta V. Yeah, so now we just solve for x, sorry. Am I rambling? So let's see, so we have delta V A 2 minus x equals 2 rho M L I arm. So then let's see, we're going to solve for x. So yeah, this goes under there, and then we say 2 minus all that. And now you see I don't have my giant boards, I've run out of boards. So I'm going to finish this algebra in my head and say x equals this goes under there, and I bring that here, 2 minus 2 rho M muscle length I arm over delta V times A. And yeah, and that's it. So now we've got it down to properties of the arm that we know, the length, the current that we measured, the resistivity of the muscle, the voltage we applied in the area of the arm, like that. Right. So then you'd say, well, wait, that's not going to tell you anything, because when I hold this thing, I don't type in, you know, what's the length of my arm and what's the area of my arm, but those are pretty standard for people. Like one of these instruments, you might put your height, and then it's going to take your height and scale it to give you roughly those numbers. These things aren't real accurate, okay, so that's how they work. So you can see, just from a single V equals IR measurement, we got IR, but we had to think about how it breaks up into fat and muscle to figure out what percent of fat we have. Now, not a lot of people have held one of these, but I do this all the time because we have a bathroom scale, not a bathroom scale, yeah, a bathroom scale, smart electronic scale. And you stand on it, you can kind of see 2 pads where your bare feet go, and you stand on it, and it magically tells you your body percentage. So how do you think it's doing that? Yes, it's a little more personal than the arm, yes, but it's basically the same thing. It's the current going, you know, through.